Hello, I'm Tim Hartley and I'm a Technical Marketing Manager working in the Media Processing Group within ARM here in Cambridge. In this talk, I'm going to look at the importance of whole system optimizing and profiling when you're developing computer vision applications. So, to start with, the briefest of introductions to Mali GPUs. The very first one, the Mali 55, was launched back in 2007. In common with other GPUs of the time, this was a relatively simple graphics accelerator, compatible with fixed function pipeline OpenGL-ES 1.1 only. Since then, things have progressed rapidly through programmable pipelines and GLES 2.0 with Mali 200 and 300, ARM's first multi-core GPUs with Mali 400 and 450, and general-purpose compute allowing heterogeneous parallel computation with the T600 and now T700 and T800 ranges. In fact, with the T604 GPU, ARM became the first mobile IP vendor to pass full OpenCL conformance, and the GPU appeared in a number of real devices, including the Nexus 10. Back then, the GPU was accompanied typically by a dual-core Cortex-A15 CPU. Moving on to today, we see mobile devices with as many as 8 or more 64-bit CPU cores, perhaps split between Cortex-A57 or 72 and A53, and an 8-core Mali T760 GPU. So the amount of raw computing power, along with a myriad of energy efficiency improvements, has dramatically changed what is possible in a mobile or embedded form factor. And this has a fundamental impact on what can be achieved in computer vision. But no matter how much processing power is available on mobile platforms, computer vision applications will use it all for some time to come. We are still in the early days of computer vision capability. If you know your graphics APIs, we are perhaps at the equivalent of GLES 1.1, a time in graphics when new features still led to strong differentiation amongst devices. Current computer vision algorithms can yield impressive results, but the rate of development of new techniques means that it is difficult to pin down all the necessary know-how into one collection of hardware IP. The flexibility of the GPU will secure its role alongside the CPU and specialist hardware DSPs for some time to come. Being able to gather detailed performance analysis for these systems is going to be ever more vital as developers seek to exploit the huge processing potential in these new systems. So, let's see an overview of the sort of heterogeneous world developers are facing. More often than not, today's mobile devices will have multiple ARM CPU cores, each with floating point vector-based Neon acceleration. This requires multi-threading to stand a chance at being optimal on multi-core systems. And for optimal use of Neon, we need to consider specific Neon intrinsics as well as vectorizing certain code paths. But the problem is magnified further with modern and future SoCs that include multi-core GPU and DSP cores capable of massively parallel operations. How we determine which parts of our applications run on which processors and which processor types is going to become a key decision in the design of new vision-based applications. An important part of that decision is going to be informed by measurements on real devices. The key is in measuring the whole system, allowing us to directly compare how our algorithms split across cores in different configurations. It isn't always sufficient to measure just one device. We need to measure how all the processors in our system work together at the same time. So as I said, we're going to concentrate on examples using multi-core CPUs and a GPU. The GPU in such a system plays a key role, and as with any platform, it's important to understand the architecture you're using if you want to get the best out of it. So let's start with a little architectural background. Here's how the OpenCL execution model maps onto Mali. Don't worry so much if you're new to OpenCL, it's not vital for understanding what's coming. Work items, individual OpenCL threads, run on the shader pipeline, each one with its own registers, program counter, stack pointer, and private stack. Up to 256 of these can run on a core at a time, each capable of natively processing vector data. We may have many millions of these threads in a single job. Collection of work items, known as workgroups, also work on an individual core. Workgroups can have barriers, local atomics, and have cached local memory. The ND range, that's the entire workload for a CL job, splits the workgroups up and assigns them around the available Mali cores. Global atomics are supported, and we have cached global memory. Relative to some other GPU architectures, Mali cores are relatively complex devices, capable of handling hundreds of threads in flight at any one time. Let's take a closer look inside one of those cores. Here we see the dual ALU, the load store, and the texture pipelines. threads come in at the top and enter one of these pipes, circle round back up to the top for the next instruction until the thread completes, at which point it exits at the bottom. We would typically have a great many threads running this way, spinning around the pipelines instruction by instruction. So let's imagine the first instruction is a load. It enters the load store pipe where it is executed. If the data is available, the thread can loop round on the next cycle for the next instruction. If the data hasn't yet arrived from main memory, the instruction will have to wait in the pipe until it's available. Imagine then that the next instruction is an arithmetic one. So now the thread will enter one of the arithmetic pipes. At this stage, it's worth going one step deeper. ALU instructions support SIMD, single instruction multiple data, allowing operations on several components at a time. On top of that, the instruction format is VLIW, very long instruction word, supporting several operations per instruction. This could include, for example, a vector add, a vector multiply, and various scalar operations all in one instruction. This can give the effect of certain operations appearing as free, as the arithmetic units within the ALU can perform many of these in parallel within a single cycle. And if that wasn't enough, we have the built-in function library, the BIFL, which has hardware accelerations for many mathematical and other operational functions. So this is a complex and capable core designed to keep many threads in flight at a time and thereby hide latency. Latency hiding is what this is ultimately all about. We don't care if an individual thread has to wait around for some data to arrive, as long as the pipelines can get on with processing other threads. Each of these pipelines is independent from the other, and likewise the threads are entirely independent from other threads. The total time for a program to be executed is then defined by the pipeline that needs the most cycles to let every thread execute all the instructions in its program. If we have predominantly load store operations, for example, the load store pipe will become the limiting factor. So in order to optimize a program, we need to find which pipeline this is, allowing us to target optimization of efforts effectively. To help determine all this, we need to access the GPU's hardware counters. These will identify which parts of the core are being exercised by a particular job. In turn, this helps target our efforts towards tackling bottlenecks in performance. Now, there are a large number of these hardware counters available. Counters for each core and counters for individual components within a core, allowing us to peek inside and understand what is going on with the pipelines themselves. We have counters for level 1 cache operations and many more. The tool I'm going to use to access these counters is DS5 Streamline, which shows a timeline representation of the program as a whole, revealing the various hardware counters along the way and a whole lot more. So here's a quick overview of DS5 Streamline. I'm not going to attempt to cover this in depth here, it would take all day, but here's a few points. Fundamentally, the tool gives us access to a range of hardware counters from both the CPU and the GPU, and even from custom sources. Whatever the source, traces appear in the same holistic view, allowing the developer to measure the system as a whole. Down here, we have traces for all the system tasks running on the CPU. Clicking on any of these isolates their contribution in the trace, allowing us to see which are having a significant impact on system performance. We can view values from the counters at any time during the trace capture, making it very simple to determine performance hotspots along the way. So, just a few of the key features of the DS5 tool. Let's look at a real computer vision case study. Here's a trace from an early build of a lane detection ADAS application from ADASWorks running on both dual-core CPU and quad-core Mali GPU. What you can see here is a whole system view. The vertical green bars in the top line show the CPU, the blue bars below that show the graphics part of the application running on the GPU, and the red bars show the compute-specific parts on the application, also on the GPU. There are all sorts of ways to customize this, and I'm not going to go into huge amounts of detail here, but you can select from a wide variety of counter information from your system depending on what it is you need to measure. Streamline allows you to isolate counters against specific applications for both CPU and GPU, allowing you to focus in on what you need to see. A bit further down, you can see the level 2 cache measurement. That's the blue wavy trace in the middle. Further down, we've got a counter showing activity in Mali's arithmetic pipelines. We could scroll down and find more, and indeed zoom in to get a more detailed view at any point. But back to this particular example. One of the things the developer was seeing with the application was a relatively high initial frame rate, seen usually for several seconds. Then the frame rate would suddenly drop in half. Now you can see we've captured the moment this happens in the trace. To the left of the vertical timeline marker, we can see the CPU and GPU working reasonably efficiently. then this suddenly lengthens out. We see a much bigger gap between the pockets of GPU work, and the CPU activity has grown significantly. The red bars in amongst the green bars at the top represent increased system activity on the platform. Well, we used this and other traces like it to feed back to the developer. It transpired that there were issues with video streaming, which was subsequently improved. So one of the benefits of having the whole system on view is that we get a holistic picture of the performance of the application across multiple processors and processor types. And this was particularly useful in this example. Now, the ADAS demo application, and this is a screenshot from it, allows some additional functionality to be enabled. Traffic lanes are being detected as before, but here the application is also tracking other vehicles it sees around the car. It can report their position and distance from our own vehicle. Here's a new trace taken with this additional feature switched on. To achieve this, another set of filters have been added to the image processing pipeline. If we look a little closer, we can see how efficiently the application is running. We've expanded the CPU trace, that's the green bars at the top, to show both cores we had on this platform. Remember, the graphics elements are the blue bars, with the image processing filters represented by the red bars. Looking at the cycle the application is going through for each frame, there is firstly CPU activity leading up to the compute job. Whilst the compute job then runs, the CPU is more or less idle. With the completion of the compute filters, the CPU does a small amount of processing, setting up the graphics render. The graphic job then runs, rendering the frame before the sequence starts again. So in a snapshot, we have this holistic and heterogeneous overview of the application and how it is running. Clearly, we could aim for much better performance here by pipelining the workload to avoid the idle gaps that we see. There is no reason why the CPU and GPU couldn't be made to run more efficiently in parallel, and this trace shows that clearly. So, how would you go through optimizing such a platform? Now, this is going to depend on the specific details of the architecture, of course, but for a Mali GPU-based system, here's a guide for the sort of things we need to think about. If we start at the top here and ask ourselves the question, are we limited by kernel execution time or are we limited by memory management? Now that's something that DS5 Streamline can show really clearly. If we decided that we were limited by kernel execution, we would then ask the question, are we then limited by arithmetic operations or memory operations? Again, those are simple counters that you can pick up from DS5. Let's assume it's arithmetic, in which case you would ask one of these three questions. Are we limited to 64 threads? Are there a large number of register bank conflicts? Or are there a large number of instruction cache misses? Again, all simple counters from DS5. If the answer to any one of those questions is yes, then you would reduce the register pressure, simplify or shorten the kernels. Then you would look at vectorizing the kernel if possible, and possibly even decreasing the arithmetic work. So you might have the option, if this was possible, to load some of the values rather than actually compute them. That would have the effect of moving some of the workload from the arithmetic part of the GPU to the load store. If we go back up to the limited by arithmetic ops question, and decided that actually we were limited by memory operations, we would then look at whether or not there were a high number of instruction reissues. The answer was yes, we might want to improve memory access, so we would look at things like data locality. If no, we would ask these two questions. Are we limited to 64 threads, or are there a large number of instruction cache misses? Again, if the answer to any of those two questions is yes, we would look at reducing register pressure or simplifying our kernels. At that stage, we would look at vectorizing the load store operations, if that was possible, or indeed decrease the memory accesses, if possible. So it might be necessary, for example, to actually recompute values rather than loading them in. Again, what that's doing is pushing some of the workload from one part of the GPU to the other. Now, if we go back to the top and decide that instead of being limited by kernel execution, we were limited by memory management, we would look at whether or not we were actually copying memory unnecessarily. One of the key things you want to aim for within any vision pipeline is a zero copy pipeline. When you copy data, it takes both time and energy. These all join up at the bottom here, and then you ask the question, well, are we now limited by the same factor that we were limited by before? If the answer is no, in other words, there's a new bottleneck, we would then reiterate, we'd go back to the top and go through this same process. If we are limited by the same factor, we are likely done optimizing. So that's a single view of the sort of process you would go through. Other platforms will likely have similar flowcharts, but with different recommendations based on the specific details of the architecture being used. The important thing for developers of modern heterogeneous vision applications is to employ these techniques from the beginning, not just at an optimization phase at the end. It might be that you cannot simply refactor an algorithm once your application is written. Doing this kind of analysis from the start and throughout helps you to determine which processor or processor type different parts of an algorithm should run on from the outset. So, how do we actually interpret hardware counters? On its own, an individual counter can tell you something, but more often than not, it's when you combine the value with others from the system where you can start deriving some real meaning. We can, for example, combine values from different hardware pipelines on Mali to determine which one is the limiting pipe. Knowing where you are limited can help in balancing the workload amongst the available pipelines. What we want to do ideally is to create new traces directly from arithmetic combinations of multiple counters. Let's look at how this works. Here we can create a new trace with 4 lines grouped into one. For each one, we define an expression that can be any mathematical combination of existing counters. For convenience here, we're going to create percentage utilization of the arithmetic and load store pipes, along with a measure of overall tri-pipe utilization and load store efficiency. Over the next few slides, I'll show you how you might then use these new combined traces. Here the trace is showing as a kernel that is bound on the arithmetic pipes. Now, we've created a rather artificial kernel, one that does minimal load store and maximum arithmetic to show this. As you can see, the trace successfully shows the imbalance between the arithmetic and load store pipes. Faced with a trace like this, the developer could comfortably move work back to the load store pipe by loading required values perhaps rather than calculating them to balance things more evenly. In this scenario, a few additional load stores are unlikely to have a material impact on the overall application performance at this stage. Now conversely, here is the opposite scenario. Here the trace is showing as very low ALU usage with maximum load store. Again, a simple artificial kernel designed to show the problem. The combined trace shows this very well. ALU usage is near minimal, with the bottleneck clearly on the load store pipe. In circumstances like this, we could add more arithmetic into the kernel without impacting overall speed. Put simply, we could do more at no additional cost. Knowing where you can add functionality like this is a powerful tool when designing complex heterogeneous applications. So what would a fully optimized application actually look like when you traced it in a tool like DS5? Here's a trace taken from an application that went through several optimization stages of the sorts outlined here. This platform has 4 CPU cores, the top green bars, and a Mali GPU shown in the red trace. We're also using the combined traces as shown before. The first thing to recognize is that the developers achieved some great pipelining here. The CPU's cores and the GPU are clearly all running in parallel. There are some interesting gaps though. Both CPU and GPU appear to be going relatively idle each frame. In this use case, the required performance was achieved and even optimized to an extent so that both CPU and GPU clocks could be reduced, saving power. Even then, there is time when the cores can be turned off, saving more power. This kind of pipelining is often achieved by the CPU and GPU processing successive frames. So for example, whilst the GPU is processing frame n, the CPU might be processing frame n+1. The key thing, as shown in the ADAS example earlier, is to minimize the time processors have to wait around for other processors to complete their jobs. So, to sum up, the computer vision use case has great potential in heterogeneous systems, but needs careful optimization to reach the performance potential a particular platform has to offer. Understanding the system you are optimizing for is key, right down to the nature of the cores you are using. Tools are vital in helping developers understand what is going on in complex systems. Viewing the processing workload as a whole, across all processors and processor types, is essential in understanding where there might be capacity to move work around the system to achieve optimal performance. Understanding the current limiting factor is key to this, and employing these tools from the outset is also important. Don't leave it to the end. It might be too late to refactor as much as you might need to. Bringing these tools in right at the start and throughout the development process can bring great benefits. So thank you for watching. I hope you found that useful. Do go to the address on the screen shown here where you can find all sorts of other useful information. Thank you very much.